Hello students, I welcome you all to my channel Engineers Academy. Do subscribe my channel if you haven't done it yet. Now we are going to solve this problem which says that the right angle boom which supports the 400 kg cylinder is supported by 3 cables and a ball and socket joint at O attached to the vertical XY surface. Determine the reactions at O and the cable tensions. So we have to find the tension in these cables and we have to determine the reactions at point O. So we have to find OX, OZ and OY reactions, and this right angle boom supports this 400 kg weight. So before applying the equilibrium conditions, we have to find the Cartesian vector representation of this T1, T2 and T3, which are the tensions in AC, BD and BE cables respectively. So this is our T1, this is our T2, this is our T3. So T1 vector can be determined by T1 magnitude times the unit vector from A to C, since T1 is acting from A to C. So this is T1 and the unit vector from A to C is the position vector from A to C divided by its magnitude. So this is T1, and the position vector from A to C can be determined by moving along X, Y and Z from A till we reach point C. So from A we need to travel this 2 meters in the negative Z direction, so I will write -2 in the K, and then from that we have to travel 1 meters in the positive Y direction, so I will write +1J, and then from there we need to travel 1 meters in the negative X. This is our positive X, so we have to travel in the negative X 1 meter, so that is -I, and its magnitude will be equal to, that is 1 square plus 1 square plus 2 square. So this will give us 1 square plus 1 square is 2 and 2 plus 2 square is 4, so this gives us square root 6. So this will give us, the magnitude is square root 6. So now from this we can write that T1 vector is, if I multiply this T1 with each and every component and divide it by square root 6, then T1 will be -1 divided by square root 6I plus 1 divided by square root 6J minus 2 divided by square root 6K. So now this is the Cartesian vector representation of T1. This is T1x, this is the component of T1 along the x-axis, this is T1y and this is T1z. Now we have to find T2. So for T2 vector will be equal to T2 magnitude times the unit vector from B to D, since T2 is acting from point B to D, and this will be equal to T2, and the unit vector from B to D will be the position vector from B to D divided by its magnitude. Now again we can find the position vector from B to D. From B we will move along the x, y and z axis to reach that point D. So from B we need to travel this 2 meters in the negative Z. So I can write that this will be equal to T2. So in the negative Z, that is in the negative K, we need to move 2 meters. So this is -2K, and then from here we need to travel this 2 meters in the positive Y direction. So I will write +2J, and there is no need to travel along the Z axis to reach that point D, so that is 0I. So I will write 0I, and now the magnitude will be 2 square plus 2 square. So 2 square plus 2 square. So this gives us 2 square root 2. So now this magnitude is 2. This is 2 square root 2. So now from this we can write that T2 vector, if I multiply this T2 with each and every component and then divide it by this magnitude, so we will have T2 will be equal to 0I plus 2 divided by 2 square root 2J minus 2 divided by 2 square root 2K. So now this 2 will cancel out, right? This 2 will cancel out with this, and this 2 will cancel out with this, so we will be left with 1 by square root 2. 1 by square root 2 and 1 by square root 2. So now this is T2, Cartesian vector representation of T2. This is the T2x, the x component of T2. This is the y component of T2, and this is the z component of T2. Now after this we need to write T3 as a Cartesian vector. So as we can see that T3 vector, this will be equal to T3 magnitude times the unit vector from B to E. So T3, and the unit vector from B to E, since this BE, this T3 is parallel to the z-axis, so T3 is directed along the negative k. So the unit vector of T3 is minus k. So we will write that this is minus T3k. So this is the Cartesian vector representation of this T3. And similarly, we can write the weight as a Cartesian vector. So weight vector is equal to, since this weight is acting in negative y direction, this is the positive y, weight is acting in the negative y, and weight is 400 times 9.81. This gives us 3924. So this is 3924, and it is acting in the negative j direction. Now since we are solving this problem by the scalar method, we are going to solve this problem by the scalar method, and we will use the moment equals to f into d. So we have to find the reactions at point O. So at point O we have to show the reactions, forces. So this will be our OX, let's say. Here we will have OY reaction, and here at O we will have OZ reaction. So we have to find OX, OY, OZ, T1, T2 and T3. So to solve this problem by the scalar method, we have to draw the orthographic projection. So first of all, we have to look into this whole system from this direction, and then we have to draw the orthographic projection. So if we look into this whole system from this direction, so we will be able to see this AB arm. This arm will not be visible since this is along the z-axis. Since from this direction we will be able to see the x and y axes. So we will be able to see this arm, which has a length of 0.7 plus 0.7. So this is 0.75. So this is 1.5. So we will be able to see the x-axis like this. We will be able to see the y-axis. This is that 1.5 arm of that right angle boom, and the weight is going to act at a distance of 0.75. So this is the weight. And T2, let me represent the components of T2. So T3, if I cut these ropes, so T2 have two components, right? As we can see that T2 has 0i, no component along the x-axis, and it has T2 has one component along the j, and it has one component along the k. So this is T2z, and it will have one component along the y-axis. So this is T2y, and it has no x component. And T3 is acting along the z direction, that is in the negative k. Similarly, T1 has three components, as we can see. This is 1, 2 and 3. So T1 has one component in the negative z, that will be T1z. As we can see that the k component is negative, then we will have one component along the positive y direction, that is T1y, and T1 has one component in the negative x, like this. So this one will be, this red component is T1x, and it is directed along the negative I direction. So we have this minus sign here. So now if we draw the xy plane from this direction, so we will be able to see this AB part of the boom, this end is B, and this end is OA, since A is visible and O, they will overlap each other, and this length is 1.5. So in the xy plane we will be able to see this T2y, T2z will not be visible. So this is that T2y, and T1y is visible. This T1y, this is the component along the y, and T1x is visible. The z component is not visible, since in the xy plane the z axis is out of the screen. So this is our xy plane projection. So now if in the xy plane, if I apply the summation of the moment about point O equals to 0, and if we assume that the counterclockwise moment is positive, so then we can see that T1y and T1x, they are passing through this point O, so they are not going to produce the moment about that point O. And one thing to remember is that T1y, the y component of T1 is 1 divided by square root 6, and here we will have T1 since we have multiplied this T1, right? So this will be T1, and this will be 2 T1, remember. Similarly, here we will have T2, and here we will have T2. So this is T1y, this T1y, this is equal to T1 by square root 6, and T2y is T2 divided by square root 2. So this is equal to this, and similarly T1x is T1 divided by square root 6. The minus sign tells us the direction. So this is the orthographic projection of this whole system when we observe the whole system from this direction. So we will be able to see the xy axes. Now if we apply the summation of moment about point O, so as we can see that this T2y is producing the counterclockwise moment. So I will write plus T2y, and T2y magnitude is T2 divided by square root 2. And this weight is producing the clockwise moment. This weight is producing the clockwise moment about point O. So I will write, and we have to multiply this T2y with its moment arm, its perpendicular distance from that point O. So the perpendicular distance of T2y from that point O is 1.5. So we have to multiply this with 1.5. Then as we can see that this weight is producing the clockwise moment, so we will write minus weight, and the perpendicular distance of this weight from that point O is 0.75. So I will multiply this with 0.75. So this is equal to 0. And if I bring this term to the other side of equation, so we will have the equation like this. And now the weight is, we know that the weight is 3924. So I will multiply this with 3924. So from this equation we can write that T2 is equal to square root 2 into 0.75 into 3924 divided by 1.5. If we cross multiply this 2 and 1.5, so we will have the equation like this. So now T2 is square root 2 multiplied by 0.75 multiplied by 3924 divided by 1.5. So this gives us 2774, or we can say that T2 is approximately 2775 newtons. So this is the tension in that BD cable. This T2 is equal to 2775 newtons. Now since we are solving this problem by the scalar method, so we have to draw the orthographic projections, or the projection of this whole system from this direction. So we will be able to see this y and z plane. In y z plane we will be able to see the y and z components only. So the y component is this OY, this T1z, and this T1y. So I'm not going to show this OX, OY, and OZ in these projections, since we are finding the moments about this point O. So if we find the moments about point O, these three reactions will not come into our equation. So only these components will come into our equation. So from this direction, this will be our orthographic projection. We will have this part of the boom, which has a length of 2 meters. And then we will be able to see this T2Z component, which is here. This red one is T2Z. Then we will be able to see this T3. So then we will be able to see this T3, since T3 is acting along the Z axis, T2Z, T2Y, and T1Y, and the weight. From this direction, the weight is acting at a distance of 2 meters. So this is the weight that is at a distance of 2 meters from the x-axis or from the point O. So now this is our YZ plane. This is our projection of the YZ plane of that whole system. So again, T2y is T2 divided by square root 2 Similarly, this is t2 divided by square root 2. This is the y component, this is the j component. Similarly, t1y is t1 divided by square root 6, and similarly the weight is 3924. So now again, if we apply the summation of moment about point O equals to 0 while considering the yz plane, so we will assume that the counterclockwise moment is positive. So now as we can see that this t3 and this t2z, they are passing through that point O, so they are not going to produce the moment about that point O. So these two components and this weight, they are producing the moment about that point O. So now as we can see that t1y is producing the clockwise moment, so I will write minus t1y into the perpendicular distance. So the perpendicular distance of t1y from that point O is 2 meters, so I will multiply this with 2. Similarly, t2y is producing the clockwise moment as well, so we will write plus t2y, and the perpendicular distance of t2y from that point O is 2 meters as well, so we will multiply this with 2. And similarly, this weight is producing the counterclockwise moment. This t2y is producing the clockwise moment, so we have to write minus sign here as well. This is minus t2y into 2, and weight is producing the counterclockwise moment, so I will write plus weight is 3924 into 2, this is equal to 0. So now if I divide this whole equation by 2, so 2 will cancel out, and from this we can write that minus t1y minus, or we can say that if you want to find t1, so then from this equation we can write that t1y will be equal to t2y minus 3924 if 2 is cancelled out. So we will be left with this simple equation, and from this equation we can write that this minus t1y is equal to t2y minus 3924. So now t2y, this is t2y, which is t2 divided by square root 2, so we will write that t2y is t2 divided by square root 2, and t1y is t1 divided by square root 6, so I will write that this is t1 divided by square root 6. And now we know the magnitude of t2. We know this magnitude of t2, which is 2775. So from this we can write that 2775 divided by square root 2 minus that weight, which is 3924. So this is minus t1 divided by square root 6. This is equal to minus 1962. So 1962, and if I divide both sides by minus 1, so this will cancel out, and t1 will be equal to 1962 into square root 6. So this will be our t1. So this answer multiplied by square root 6, this gives us 4805. So t1 equals to, let me write that t1 is equal to 4805 newtons. So now we know t1 and now we know t2. Now to find t3, we are going to consider the xz plane of that system. So we have to observe the whole system from this direction. So if we observe the whole system from this direction, so we will be able to see the xz plane, and then we will be able to see all the components along the x-axis and along the z components, and the y components will not be visible since the y axis will point out of the screen. So we will be able to see this t2z and this t1z, and the weight will not be visible since it is acting along the y, and similarly this t1 axis, this will be visible. So this is our xz plane, t2z, t3 is also visible since t3 is acting along the z-axis, t1z is visible and t1 axis is visible, and similarly the weight is not visible since the weight is acting, the x-axis, the y-axis is out of the screen and the weight is acting into the screen, so it's not visible in this xz plane. So now for xz plane, again we are going to apply the summation of moment about point O. Again this will be equal to 0 since the system is in equilibrium and the counterclockwise moment is assumed to be positive. So now as we can see that this t1z, this is passing through that point O, So it's not going to produce the moment about that point O. So these two components and this T1x, they are producing the moment about point O. So T3 is producing the counterclockwise moment. So I will write T3, and the perpendicular distance of T3 from that point O is this distance, which is 1.5. So I have to multiply this with 1.5. Similarly, this T2z is producing the counterclockwise moment, and its perpendicular distance from that point O is 1.5. So I will write plus T2z into 1.5. And similarly, this T1x is producing the clockwise moment about point O, and its perpendicular distance from that point O is this 2 meters distance. So I will write minus T1x into 2, this is equal to 0. So now T1x is this is T1x, this is T1 divided by square root 6. So let me write that this T1x is T1 divided by square root 6. Similarly, T2z, so T2z is, this is T2z, which is T2 divided by square root 2. So T2 divided by square root 2, this is T2 divided by square root 2. So now if I divide this whole equation by 1.5, so this will cancel out, this will cancel out, and we will have 1.5 here. And similarly from this we will have the equation like this, and from this we can write that T3 will be equal to minus T2 divided by square root 2 and plus T1 into 2 divided by square root 6 into 1.5. So now we know T1 and T2. T1 is 4805, so we can replace this T1. We can write that this is 4805, and similarly T2 is known, which is 2775. So I will replace this T2 by its magnitude, which is 2775. So this will give us T3, everything is known. So this is minus 2775 divided by square root 2 plus 4805 into 2 divided by square root 6 multiplied by 1.5. So this gives us 653. So this is 653 newtons. So this is T3. So this is T3 magnitude. Now we know the tension in all the cables. This is T3, this is T1, and this is T2. Now let me copy all these forces, since we are going to apply the summation of forces along the x, y, and z axis to find this OX, OY, and OZ. So we need to have these equations. Now these are all our vectors, Cartesian vectors, and now to find OX, OY, and OZ, we have to apply the summation of forces along x. That will be equal to 0. So as we can see that we need to add all the x components of T1, T2, and T3 and the weight. So the x component of T1 is this is minus T1 divided by square root 6. Then we have this 0i, this is plus 0i, and then we have in the x direction we have OX. So remember that reactions now, that is OX. So we will write plus OX. There is no need to write this I in this equation. So this is equal to 0, and from this we can write that OX is equal to T1 divided by square root 6, and T1 is 4805. So this is 48. So OX is 4805 divided by square root 6. So this gives us OX equals to 1962 newtons. Similarly, if we apply the summation of forces along the y-axis is equals to 0, that will be equal to 0 as well, since the system is in equilibrium. Now we have to add all the j components. So this is T1 divided by square root 6. So T1 is 4805 divided by square root 6. Then the j component of T2, which is T2 divided by square root 2. So this is plus T2 divided by square root 2. This is T2 divided by square root 2, and we know T2, which is 2775. So this is 2775, and similarly T3 is only acting in the k direction, so its j component is 0, and the weight is acting in the j direction, so you will write minus 3924, and in the y direction we have OY, so I will write plus OY, and this is equal to 0. So now we can add all these. This is 4805 divided by square root 6 plus 2775 divided by square root 2 minus 3924. So this gives us approximately 0, right? So since the difference is very small, this is 0.14, and this difference is due to the rounding of the values, right? But this difference is very small, so we can say that OY is approximately equals to 0. Similarly, if we apply the summation of forces along the z-axis is equals to 0, so then we have to add up all the k components, right? So T1, the k component of T1 is 2T1 divided by square root 6, and it is acting in the negative direction, so we will write minus 2T1 divided by square root 6. Now T1 is known, which is 4805, so we will multiply this with 4805. Similarly, the k component of T2, this is minus T2 divided by square root 3 minus T2 divided by square root 3. This is square root 2, remember, this is not square root 3, this is square root 2. And T2 magnitude is 2775. This is T2 magnitude, which is 2775. So this is 2775. And now T3 is acting in the k direction, so we will write this is minus T3, so minus, and T3 is known, which is 653, so this is minus 653, and then we will have plus OY, we will have OZ. So OZ is acting in the z direction, so this is plus OZ, and this will be equal to 0. So from this we can write that if I bring OZ to the other side of equation, so we will have minus OZ, and if we multiply this whole equation with minus, so this will become positive, this will become positive, and this will become positive, and similarly this will become positive. So this gives us OZ equals to 6538 newtons approximately. So the reactions at the ball and socket joint is OX is equal to 1962, OI is approximately equal to 0, and OZ is 6538 newtons. And similarly, T1 is 4805 newtons, T2 is 2775 newtons, and T3 is 653 newtons. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems related to engineering statics.